Good afternoon, students, and I will continue talking about growth of nanocrystals. But now we will talk about growth of nanocrystals inside of the glass matrix. So, first of all, what do you know? What is glass? Glass is a solid amorphous material that sometimes can be considered as the undercooled melt. The main features of the glass is that its melting point is not defined. The transition between glass and liquid is continuous, and during this transition, all physical properties of the material are changing continuously, in particular viscosity, which is the main characteristic of the glass. If we look at this phase diagram of glass, we will see that at high temperatures the constituents of glass are molten and in the liquid phase. But while we decrease the temperature of this liquid, the volume of this liquid also decreases, but at the same time its viscosity increases. When we are reaching the temperature that are assigned as T melt, the possibility of crystallization starts to exist in connection with a strong change of volume. Sometimes the crystallization can be observed at this temperature, but at a very slow cooling rates. If we still have very rapid cooling rates, then no crystallization will occur, and the glass remains at a metastable thermodynamic state of the undercooled melt. With further decrease in temperature, the viscosity still increases in such extent that the molecules of the melt can no longer arrange themselves in the equilibrium state. And then viscosity of this material reaches the value of 10 to the 12 power pascals. It means that glass transforms finally to the solid configuration. The temperature that attributed to this transition is called glass transition temperature. And I want to emphasize that glass transition temperature is always connected to the viscosity of the glass, which is equal to 10 to the 12 power. But depending on the glass composition, glass transition temperature can differ in the range from 350 degrees up to 500 degrees Celsius. While cooling down of the glass down to the room temperature, we obtain the viscosity of the glass from this range, which is also depends on the glass composition. So, what about glass composition? The glass constituents are divided into two big groups: network formers and network modifiers. Network formers are mainly oxides. These are molecules that form the structure of the glass. And the main network formers are silicon, aluminum, and boron oxide. They are widely used in producing glasses, and namely commercial glasses. The main difference between these network formers is their melting temperature. Silicon dioxide has one of the highest melting temperatures. That's why fully pure silicon glasses are not really widespread nowadays, because we have to synthesize them at really very high temperatures. That's why the most widespread glasses now are borosilicate glasses. They have a little or not little impurity of boron oxide inside of the silicon oxide, and this impurity of boron oxide decreases the melting temperature of the glass, thus making it comfortable to use and to work with. So, combining different network formats, we can create such material with the desired melting temperature, and it means with the desired glass transition temperature. Network modifiers are usually used to enhance the chemical durability of the glass, but nevertheless, the most widely used network modifier is sodium oxide. It breaks the bonds between silicon and oxygen atoms inside of the silicate glass matrix. The viscosity of the glass and the diffusion velocity of ions inside of the glass matrix are mainly influenced by the network modifiers. The temperature range of the annealing can be derived from the range between glass transition temperature and glass melting temperature. Here in the table you can see the example of the glass composition, namely borosilicate glass composition, which is doped with cadmium selenide and cadmium sulfur compounds. This is the melting temperature of this glass and the heat treatment temperature of the glass. As you can see, it can be used 1- and 2-step annealing here. The glass matrix represents a confining barrier material for small semiconductor nanoparticles. So to estimate the height and the form of this potential barrier, we have to obtain the absorption spectra of the undoped glass and doped glass with semiconductor ions. But as you can see here, it is really difficult to define the energy gap from the onset of the absorption age. That's why for many applications the assumption of the infinitely high barriers of the undoped glass is a justified approximation. But after the addition of semiconductor components, the absorption age of glass shifts to the smaller energies because of the appearance of the impurity levels of the semiconductor ions inside of the band gap of the undoped glass. Also, semiconductor ions can provide a long absorption tail that even reaches the visible spectrum. That's why infinite barrier is no longer a good approximation to the doped glass. But what is the most suitable heat treatment? 1-step, 2-step process? What temperature should we take to obtain semiconductor nanocrystals? The first experimental proof of the Lifshitz-Slozov distribution of sizes was obtained by Ekimov. And here you can see it in the picture. Ekimov showed that even at very small sizes of nanocrystals, so about 5 nanometers, the dependence between nanocrystal size and duration of heat treatment in this axis will be a linear function, which proves that the last stage of nanocrystals growth was coalescence stage. But if we use 2-step process, at first step the glass is heated for several hours at temperatures that are slightly above glass transition temperatures. This step increases only the number of formed nuclei, but no changes or minor changes in final sizes and size distribution of nanocrystals could be measured. Difference in the temperatures of the first and second step should be more than a few hundred degrees. When temperature between these two heat treatment stages differ only by some tenths of degrees, a small improvement in sizes and size distributions could be observed. But if we are talking about growing the nanocrystals by realizing a diffusion-controlled precipitation, then a well-known asymptotic distribution function will be obtained. Its advantages is that it is independent from the starting conditions and it fixed at its half width, which is very small. But the main disadvantage of the one-step process is that this growth process doesn't result in very small nanocrystals. So, growing nanocrystals in a glass matrix, during this we have only two ways. First way, to grow nanocrystals with a very small mean size, but with a very big size distribution in a Gaussian form with deviation of sizes of about 30 or 40%. And the second way is to grow nanocrystals with a very narrow size distribution, but with a very big mean size. But what if we want to obtain nanocrystals of small mean size and with small size distribution? The method called growth neonucleation can be used. From the previous lecture, we know that the critical radius of nuclei and the nucleation rate are determined by the supersaturation rate and the surface free energy. In glass, these two parameters can be controlled by the semiconductor ions concentration and the matrix composition. Therefore, we should provide one-step heat treatment at very low temperatures, thus providing low diffusion coefficient, and at very low concentrations of semiconductor ions to prevent the competitive growth of nanocrystals. The results of such growth neonucleation of cadmium selenide quantum dots in borosilicate glass you can see here. Here is the absorption spectrum of the glasses after different heat treatment regimes that can be seen here. The most intensive absorption spectra we got after this regime of heat treatment, and at the same time this regime provides the absorption spectrum with the smallest half width of the absorption band. So what is the correlation between the heat treatment regime and the size distribution of the nanocrystals? We took two different samples from the previous slide with these heat treatment regimes and used small angle X-ray scattering to obtain size and size distribution inside of these samples. As we can see, comparing these two different heat treatment regimes and samples after them, we can see that the mean radius of the nanocrystals are nearly the same in both cases. But in the first case, we see that we have almost symmetric size distribution of nanocrystals with a very small half width. It means that this heat treatment regime coincides the first stage of nanocrystals growth near the nucleation stage. That's why we see the symmetric size distribution. And the maximum of this size distribution is situated at about 1.6 nanometers with a half width of 0.2 nanometers, which is the 13th% of deviation of size. This is very, very small value. But if we are talking about second case and second heat treatment regime, we see that the size distribution is asymmetric. So it means that we are still at the beginning of the competitive diffusion controlled growth of nanocrystals, but not at the end of it, because the size distribution has not the form of pure Lifshitz-Lozov function form. So it means that if we are talking about glass and a growth of nanocrystals inside it, if we want to obtain the nanocrystals of very small mean radius and with the very small and very narrow size distribution, the method of the growth neonucleation is one of the most simplest methods that we can use. But if we talk about glass matrix, what if we want to prepare another type of nanocrystals inside of the glass, namely the nanocrystals of copper halides? The main differences of these nanocrystals from the previous type is that they have really low melting temperatures, about 400 degrees. But if we are growing these nanocrystals inside of the borosilicate glasses, the heat treatment temperatures are still determined by the glass transition temperature. So it means that the heat treatment temperatures are lying in the range between 500 degrees and 600 degrees Celsius. It means that during their growth, crystals are still in the liquid state. And the second feature of these types of nanocrystals is that their thermal expansion coefficient is bigger than that of the glass matrix. It means that during cooling the glass sample, the nanocrystals inside of the matrix will shrink in more extent than the glass matrix around them. And they might appear that after cooling down to the room temperature, they will be inside of the pore with the sizes more than the sizes of nanocrystals. A vacuum pore inside of the glass. Isn't it fantastic? Thank you for your attention and goodbye.